In this video, we're going to be talking about the average value of a function. Example 1 says, suppose that you have an incubator. Often used in laboratories, an incubator is an insulated box used to grow and maintain microbiological or cell cultures by maintaining certain temperatures. And every 2 hours, starting at noon, you check its temperature. Find the average temperature. So we have our data points in a table as well as in a graph. And if I wanted the average temperature, which I'll denote with capital T sub AVG, that is equal to, I'm going to take the 5 temperatures that we have, -2, 0, -1, 3, and 2. And then because I have 5 data points, I'm going to divide by 5. And -2 plus 2 is 0, and we end up with 2/5, or in other words, 0.4 degrees Fahrenheit. So that is our average temperature. Now, what if we had a temperature reader that records the temperature of your incubator at every instant during those 10 hours? How would we find the average temperature? There would be infinitely many data points. Suppose f of x represents the change in temperature with respect to time. To find its average value on the interval from 2 to 10, divide the interval into 8 subintervals of length 1, then pick a temperature in each interval, add them together, and divide by 8. So this tells us that the average value of our function is 0.375 degrees Fahrenheit. Note here that we just used the left endpoints for each interval when we calculated the average above. But notice here, so we started at 2 and then ended at an input value of 10, and we essentially created rectangles. And so that's how we were getting the values that we had here for our average. If we decided to divide the interval a to b into n subintervals of equal length delta x, which is equal to b minus a over n, which also implies if I took this equation and I solved it for n, that n is equal to b minus a over delta x, and we chose our sample points x1 star, x2 star, all the way to xn star in each subinterval, then we would have the following. The average value of our function would be approximately equal to the summation of all of the output values divided by the number of data points that we have, which in this case, we said earlier, n is equal to b minus a over delta x. And right now I have a complex fraction, so what I'm going to do is I'm going to take my denominator, take the reciprocal of it, and then multiply. So now that would leave us with delta x over b minus a times the summation that I had earlier. Now, because delta x is a constant with respect to the summation, what I can do is I can put my delta x value inside of my summation, and here I'll just put a 1. Now, as we increase the number of intervals and as the width of the intervals gets smaller, our estimation gets closer to the actual average temperature. Essentially, we want to take the limit as n approaches infinity, like we have previously. So we find that the average value of our function is equal to the limit as n approaches infinity of the quantity that we just wrote, 1 over b minus a, times the summation from I equals 1 to n of f of x sub I star times delta x. Now, in the eyes of the limit, or with respect to the limit, 1 over b minus a is a constant. So what I can do is I can factor out 1 minus b over a outside of the limit. And then now we have the limit of the summation. And this should look familiar at this stage. We've dealt with this many times. This thing here is, as the limit as n approaches infinity, that just turns into the definite integral. So finally, we have that the average value of our function is equal to 1 over b minus a times the definite integral from a to b of f of x dx. So let's use that formula that we just derived to help us with example 2, which says find the average value of the function f of x equals x squared on the closed interval from 1 to 4. So just as a visualization of what we're doing, here's my y-axis, here's my x-axis, and I'm looking at the function y equals x squared, and I'm looking at it between 1 and 4. So I know that when I plug in 1 into my x squared function, my output is 1. And when I plug in 4, my output is 16. So I want to find the basically average y value on that curve between x equals 1 and x equals 4. And if it helps you, you can think about this as a function that models something like, maybe that's the amount of money in my bank account after X number of days. So on day 1, I have $1 in my bank account, and on day 4, I have $16 in my bank account. So between day 1 and day 4, on average, how much money do I have in my bank account? And we said earlier that the average value of the function was equal to 1 over b minus a times the definite integral from a to b of whatever our function is. So here our b value is 4, our a value is 1, and then I'm going to multiply that by the definite integral from 1 to 4 of x squared dx. And that fraction is going to simplify to 1/3. The antiderivative of x squared is x cubed over 3, and I'm evaluating this between x equals 1 and x equals 4. If I multiply 1/3 and 1/3 together, that's going to give me 1/9. And then I have 4 cubed minus 1 cubed, and that gives me 1 over 9 times 64 minus 1, which is 63, and that turns into 7. So 7 is the average value of my function, and if you think about this in terms of the bank account, that means between day 1 and day 4, I had an average of $7 in my bank account, which is a little sad, but that's reality sometimes. So this question says, do you think that there's a specific value c such that f of c is equal to the average value of the function in the previous example? And the answer should be yes, because f of x equals x squared is a continuous function. So I don't know exactly where it is, but here's 7, and that means that I should be able to plug in some value c where it's going to give me an output value of 7. And really, I actually do know what it is, because what we can do is we can take our function and set it equal to 7, and then that's going to imply, if I take the square root of both sides, that x is equal to the square root of 7. So this c value right here is the square root of 7. And that leads us into the mean value theorem for integrals, which says, if f is continuous on the closed interval from a to b, then there exists a number c in that interval such that f of c is equal to the average value of the function, which we already know from earlier is equal to that thing. Or alternatively, if I take f of c is equal to this thing, and I multiply both sides of the equation by b minus a, that gives me this alternative version of my mean value theorem for integrals. Example 3 says, consider the function f of x equals cosine of x on the interval from 0 to pi over 4. Part A wants us to find the average value of f over the given interval. So again, just a visualization. Here's my y-axis, here's my x-axis. Cosine starts at the peak and goes something like that. This value, we know that cosine is equal to 0 when our input is pi over 2. Here's pi over 4, and we're looking for the average value of our function between 0 and pi over 4. So that is equal to 1 over pi over 4 minus 0 times the integral from 0 to pi over 4 of the function cosine of x dx. If I simplify my fraction, we get 4 over pi, and then the antiderivative of cosine is sine of x. And I'm evaluating this from x equals 0 to x equals pi over 4. That's going to end up being 4 over pi times sine of pi over 4 is root 2 over 2, and sine of 0 is 0. So that's going to simplify to 2 root 2 over pi. So that means that somewhere like here, we have 2 root 2 over pi, and that's going to be somewhere like there. I drew it a little high. And so part B says find a value c that is guaranteed by the mean value theorem for integrals. So we're trying to find this x value here. We might call it c or question mark or x, whatever you want to think about it as. So maybe I'll put c here. And so what we want to do is we want to take our function and we want to set it equal to 2 times the square root of 2 over pi. And I'm trying to solve for x, so what I'm going to do is I'm going to apply cosine inverse to both sides. And this is the value that is going to give us our average value if we plug it into our function.